It's like, it's not my bed. This is. I'll show you this.
Yeah. Okay, so it's nice that it's there. I'll bring the only one. Right. Yeah. Yeah. It's. What is that?
Okay, did I talk through the calendar with you, walking through? I did, okay. Is anyone not get the calendar from Friday? Everyone has it? Okay, page 13. All right, so we have a table of values. We have a graph. We have a function defined by f of x. G is a differentiable function that just tells us that our g function is smooth curve all the way through. No sharp turns, no holes, no asymptotes. And then the h function has 5 line segments, which means that everything here is just going to be nice geometric shapes where, we're asked to find the area or involving the integral. We can do that since these are all nice geometric shapes. Basically, all of this we can fit under either shape as a triangle, a square, or a rectangle. All right, part A. Find the slope of the line tangent to the graph of f at x equals pi. So here's our f function. So if I want to find the slope, I have to find the what first, though? Well, it's just ask for the slope, not the tangent line equation. Find the what? Derivative, yeah. So we have to fill the derivative, and then from the derivative, we can plug in pi, and that'll get us our slope value. Okay, so let's find f prime. Cosine 2x becomes 2. Right, yeah. Chain rule, a little bit of chain rule, negative sine of u times u prime. Eventually, I'm going to pull that 2 out in front. We don't want to let that 2 and 2x come to be together because that 2 is outside the trig function. Okay, and then e to the sine of x. Remember, this is e to the u, right? What's e to the u's derivative? Okay. So e to the sine x times cosine. Cosine is my u prime, yeah. Okay. Now that we have our derivative, how can we find the slope? Plug in what? Plug in pi, yeah. So see if we can get this down to a cleaner answer. All right, what's sine of 2 pi going to be? Same thing as sine of 0, right? Sine of 0 is 0. E to the sine pi. Sine pi is also what? Also 0. And then cosine of pi is -1. So therefore, my f prime of pi is just equal to what? -1. E to the 0, anything raised to 0 power is 1. Okay, next part. Let k be defined as k equals h of f of x. Find k prime of pi. Before we can plug pi into k prime, we first have to find what? What's our first step? Derivative, yeah. But look at how k of x is the chain rule, yeah. Remember, it looks kind of like product rule, but it's not, right? Product rule will be h of x times f of x. If there's only one x that means it's a function within a function, we gotta go through chain rule. Okay, so try that first. See if you can do chain rule on your own before I go over it with you. Outsize derivative times insize derivative. Go ahead and replace every x with pi. Okay, make sure you go slow through your evaluation. We're not going to do this in one step. Okay, so you're going to kind of gather information as you go along, and eventually you're going to be able to get to the point where you're going to get down to a numeric value. Okay, what's something that we can find first that's manageable? Okay, f prime of pi. We have that data, right? What's f prime of pi? -1, so that we can do. What else can we find? F of pi. We got to plug that pi into the f of x function, right? So into the original function. So we have to kind of step off to the side here and find that information before we can plug in. So f of pi just means plug pi into my original f of x function. So cosine of 2 pi plus e to the sine of pi. Cosine of 2 pi is zero. Cosine of 2 pi is the same thing as cosine of 0. 1. Okay. E to the sine pi. Sine pi is e to the 0 is 1. So 1 plus 1 is 2. So now that I have f of pi, we still have a little bit more to do, but at least we have this piece covered. And now what's the last thing that we need to find? H prime of 2. H of x is here. H prime of 2. We know 2 is here. But it's not asking for the point, right? It's asking for what? The slope, right? And what's the slope of this line segment? Good. It's a negative slope because from left to right, the graph is falling. So down 1/3, negative 1/3. And what's our overall answer going to be? K prime of pi equals 1/3. Negative times negative, positive. Part C, let m be the function defined by m of x equals g of negative 2x times h of x. Find m prime of 2. Before I can find m prime of 2, I first have to find what? Before we can involve 2, we first have to. Or what would your first step be? Would you just plug 2 into m of x and get m prime of 2? We have to find the what? find the derivative, right? And prime of x. So what, look at how m of x is look at how it's formed here. What do we have to go through if we want to find the derivative? You have negative 2x times h of x, what would you use? Would you use chain rule again? Would you use quotient rule? Product rule, right? Product rule, because we have g of negative 2x, that's one expression. H of x is a different expression, and they're being multiplied. So anytime you see multiple x's in function notation, it's going to be different than just one x in function notation, right? This is chain rule, but this is product rule. So we have f and g, f prime g plus f g prime. We label the parts of product rule here. Right, what's g of negative 2x going to become? What's the derivative here? Now this part, we do have a little bit of chain rule because there's portions inside the parentheses. So g of negative 2x becomes what? What's outside's derivative? G prime of negative 2x times inside's derivative, negative 2. Negative 2x becomes what? Negative 2. Okay. Times g, which is the original second expression. Back to f, which is my original. And then g prime. Now what can we do? Would this be our answer here? Simplify? What would you do next? Would you simplify this? Well, what's our goal here? Plug in. What? 2 and 4 x, right? Can we leave our answer like this, or do we have to go any further? Okay, we can find all these, we get all these function notations into numeric values, right? Okay, so g prime of negative 4. Where can we look for that? Look at the table. H of 2. Yeah, we're gonna have to kind of estimate here. So the slope is negative 1/3, so it's negative 1/3, negative 2/3, negative 1. So negative 2/3. G of negative 4. What you get? 5. That's for the table. And then h prime of 2. We found this before, right? Negative 1/3 slope. So this answer is fine. Remember on AP exam, anything simple, anything unsimplified, as long as they're numeric values, won't lose a point. So I'm just going to just go ahead and clean this up, though. but you don't have to go this far. This is fine as well. Part D, is there a number C on the closed interval such that G prime of C is equal to -4? So the first thing, our natural initial step is to look at G prime and see, do we see G prime -4 show up? Do you see anywhere where G prime is equal to -4? No. But we can't stop there, right? Maybe we should be using G of X instead. So if I want to use G of X to see if there's a G prime of a certain slope, what is that? That they're trying to get us to use what? Using the function, not IPT, close. MBT, yeah, that's mean value theorem. So mean value theorem says, can we find the slope at the order pair level? If the slope at the function level is equaling -4, then we can guarantee that that slope value -4 will show up somewhere along that curve. So mean value theorem says, well, here's the original mean value theorem. F prime of C equals f of B minus f of A, or B minus A, but we can just adapt it for our G of X function. G of B minus G of A over B minus A. So we're going to first start off here. Can we find the slope between the two endpoints? If the slope between the two endpoints matches -4, then, right, if my two endpoints is producing a slope of -4, then there must be a place on the curve where the curve is also experiencing that value, that slope value of -4. Okay, what can I plug in for A and B? Yeah, the endpoints are provided here. So A is -5 and B is -3. Okay, so G of -3, we go to our table. G of -5, we go to our table. Are we able to get that -4 that they're asking for? Yes. So the slope between the two endpoints is producing -4. So if there's a slope of -4 between the two endpoints, there must be an exact slope of -4 somewhere along the curve, as long as our function is continuous and differentiable, which it is, right? They say that G of X is a differentiable function, which assumes continuity. The mean value theorem, since the slope between two endpoints produces -4, there must be a value of C where G prime of C is equal to -4. And to the side, we just also list out our conditions. We know that our G of X is continuous, bracket, -5 to -3, and G of X is differentiable, parentheses, -5 to -3. Okay, page 14. Let k of x equals f of g of x. Write the equation of the tangent line to the graph of k at x equals 3. So now it's asking for tangent line equation. So what information do we need for tangent line equation? Open point. So point, we can just plug 3 into the k of x function. To find the slope, we got to get to the derivative. To get to the derivative, look at how h of x is set up. We got to go through what rule here? Chain rule. Okay. So let's get our order pair and slope through chain rule. Outside derivative times inside derivative. Let's find one piece at a time. You're not going to do all this in one step. Get 3. I can choose a table to find that. F prime of 6, go to our table again. G prime of 3, also table. We have our order pair, we have our slope. Point slope form. Right, so G of 3, you're good with that being 6.
And is that 6 cubic towards G of 3 and then graph x is 6?
G of 3, that's right. Yeah, so all these are the values, you're right. And then these are the x values. So G of 3. And then F prime of 6. Also the table, right? That's equal to 5.
Yeah, why wouldn't that also be like going back to find the x, like, then by the G of 3 was?
Well, this is a function within a function. So we found G of 3, right? G of 3 is equal to 6. But now what's left is we're needing to find F prime of 6. So F prime of 6, we go to our F prime table.
Yeah.
F prime of 6 equals 5.
Okay.
So now, yeah, so the y value all of a sudden becomes the x value within this context. Oh, 10 times x minus, wait, did I mess up here? K of 4 plus. My bad, it's 3-4, not 6-4. So what you guys were, sorry about that. I was looking at that 6 here, but my order pair is 3-4. Okay, part B. H is defined as G over F. Find H prime of 1. It's asking for the derivative and then plug in the point. But to build the derivative, look at how H is designed here. We got to go through what? The other one, push rule. But remember how we learned push rule is F prime G minus FG prime over G squared? Everything is backwards here. So, just be aware of that. I'm assigning F and F prime to be the numerator, and G prime to be the denominator. So all of our denominator squared. So just understand that our G is F and F is G, basically. Right? Replace every X with what? With what? X with 1, right? Find H prime of 1. Okay, quotient rule, plug in all the X's with 1s, and then use the table to fill in all the numeric values. Part C, evaluate the integral from 1 to 3 of F double prime of 2X. Okay, process we have to go through here. Substitution, or U value being what? You need to keep track of what in front. Okay. Okay, so ready to evaluate. What do you know about f del prime of u integral? What will this turn into? F prime, yeah, you're just making it go up one level. Okay, do we do plus c here? Why? There's bounds, okay. Are we ready for bounds at this moment? Okay, what needs to happen? Bring back your x, and then you can do your half bracket, and then start working the bounds in. And make sure that you're doing that transformation that's required, because if we want to drop that integral, we got to do the antiderivative. There's going to be something that's going to change with what we see here, and that changes with the function. Second derivative, antiderivative is going to bring us up to f prime. Now, upper and lower bound can be involved. Okay, if you evaluate it, can we stop here? One step further, right? Table of values. If they gave us table of values, we have to get it out of function notation into numeric value before we stop. Fine. Or you can do 5/2. Unsimplified is fine. Okay, next page. G of x equals f of x quantity squared. Find the instantaneous rate of change of g at x equals 9. So what does this mean? Yeah, slope, derivative. Right. If I want to find the derivative before applying the slope, what do we have to involve here if we want to find the derivative? Okay, yeah, outside, inside portion here. So the outside is that bracket squared. Inside is that fx, and we're just taking turns building each derivative one piece at a time. Okay, so bracket squared, what derivative is that? Power rule, right? 2 bracket to the first power, right? Imagine this is x squared. X squared would be 2x. Parentheses squared, which would be 2 parentheses. What goes inside the parentheses? Do we put f prime in here? Just f, okay. So we're not doing the inside yet. Now that we're done with the inside, sorry, now that we're done with the outside, we're moving on to the inside. F becomes, now you have the derivative. Now you can plug in 9 and for all the x's, clean that up. Part C, find the slope of the tangent line, same process, derivative, then plugging the three. Look at how K of X is, defined here. What derivative rule do we have to go through here? Product rule, yeah. These are two distinct separate functions that are being multiplied. We got to go through product rule. Okay, what's f of 3x going to turn into? Yeah, a little bit of chain rule here. F prime of 3x times 3. G stays the same. Back to F. And what's G prime going to be? 2x, yeah, just power rule. Right, that's the hard part. Now you're just replacing all the x's with 3's and trying to get your function notation to numeric values before you stop. But you can leave your answer unsimplified. This is fine as well. All right, what's needed for part D? Yep, try that. So you can go through those steps. Let's evaluate the integral. What's going to happen with f over prime? Turn into what? Prime. No plus c because we have bounds involved, but we're not quite ready for bounds until we do what? Now let's bring our x's back. Now our bounds can play a role. Okay, let n of x be equal to 0 to x squared of f prime. Okay, evaluate n of 3. N of 3, we're just going to plug directly into our formula here. Now, do we have f prime that we can find the area under the f prime graph? There is no f prime available, but can we turn this into something else that we can allow for us to use our f of x? What do you know about the integral of f prime? Guess what? Just f, right? Just like the previous problem, right? The integral of f double prime becomes f prime becomes f. So in this case, we're transforming it because we don't have f prime to find the. I mean, if we had an f prime graph in front of us, then we can add up those areas, but we don't have it. But what we can do is we can change it into f of 9 minus f of 0, right? F of x with brackets from 0 to 9. And this we can do because f of 9 is a value from our table, so is f of 0. So f of 9. I'm sorry, f of 9 is -2. First row. Okay. Before we can find n prime of 3, first I have to get to n prime of x. To get to n prime of x, that means I have to find the derivative of that expression. All right, look at this notation here. What does this remind you of? Second theorem, right? So we know those two cancel out. What happens to the upper bound? Yep, so f of x squared. But this is more than just the 1 here, so times what? What's the derivative of x squared? 2x, right? So it's f of p of x times p prime. Remember, that's the second theorem. So f of x squared times 2x. So now it's easy. You can now plug 3 into n prime. Oh, f x squared. I'm sorry. This started off with f prime. I forgot to include that. That was f prime to begin with, so f prime needs to stay because it was part of the original definition. I just forgot to include that. -4 times 6 is -24. All right, your homework is just to finish page 16. Tomorrow I'll check page 13 through 16. I'll send out a reminder this afternoon. Okay, great. Thank you. I want to be there. Yeah.
I have not touched it. Oh. Yeah. Like, literally, they give that, if I get that, that's like 8:25. Great day, guys. By the way, I look like 5. Class, like 3.
What we do is like we grab the board the first like. First few
Yeah, I think, our people was, but I'll let you know.
So. I realized the first grade, that's what I was trying Sorry.
Oh, that's fine. Bring your book back.
So I already took it. I just Thursday.
Thank you. Thank you.
Well, it won't back up.
Take that back. That's next period.
Okay, sounds good. Thank you. Hey, Sarah, how are you? Good.
With my packet.
Okay.
And I was out the day that you checked me.
Okay. Okay, great. Thank you. Yeah, you say your thing. We can hear.
No, we're gonna take.
I traded. So that's money. It might have been my bag.
Like, can't believe. You're going to parking lot.
Yeah, like, you got it. Right, you the last page.
I know. But and that's really like, you're doing my.
We'll talk about it.
I don't care.
Today, absolutely. Is it good or bad? Did I have it? Actually, a good short.
I mean, it's like,
I'm gonna walk in. Well, to the wall here now.
you will.
I
No.
I must still like, I'm like, I can't do it.
Oh,
You did.
did you guys go? Why don't?
Okay, is it formatted like this or more like? Yeah. It doesn't, but sometimes you have to get the option of deciding which one to choose. Like, sometimes problems will say, choose two options here, other times it'll say, let me see. No, it won't be formatted like this, yeah. Where it's going to try to say which test to use. Yeah. What do you want to take?
I get a lot of them.
Actually, it's really my, I will have it in my discussion.
Yeah, but I think he's very. The intro.
I know, I feel like my part. Was like, you know. I think it's like, what's that area? Honestly, I don't think really good. No, it was just like, well, easy. We had to wait, we had to take, like, I know. It's too, I have to do so. Yeah, but like.
I know. Like, that'd be really good.
You would always.
Yeah, like, black and white. Yeah, wait, I do Wait, why do we not there? We all.
Okay, in your pack, AP packet one, the text here in your 10 through 16.
Yeah, like, so.
Are y'all taking my class?
Yeah.
Yeah, that big, I should put it on. Yeah, like, shows.
It's my brain.
Never been on a vacation with a wood.
That would be fun, yeah.
Oh, I didn't know.
Like, I have a problem because some. Almost done. My car is yellow.
You can't like plug it into the generator, once it's like you let it, you know. Just like any of those, yeah.
Yeah. And then you're thinking, yeah, during this, topic. So you're like.
Okay, so yeah.
Yeah, I haven't even done one.
Yeah, I don't.
Yeah.
I don't have
I've never done one. Appreciate having a chair, not That's one thing I'll be honest, you will try to see the video.
Right now, I have a.
There's like, we like one, big, big. No, okay, I got.
What if I third degree has a?
Oh, she wrote all of it, right?
Like, I don't know. There was some change. I hope everything works out.
Bring young, but she looked, we should get for any, but me, it was kind of thirty.
Oh, that was.
But she don't want to. Or
Yes, I are.
For me, like, I feel like I have to know, like, I feel like daily know three. Not walking in.
I feel like I had.
Okay, let's go to page, 17. So your quiz on Friday, will be one, Taylor series FRQ and one, particle motion parametric FRQ. I think we've gone through all the variations of parametric, FRQ, between pages 7 through 13. So I think those will be good ones to review. I will have a help session, Thursday, morning, but I'll also, give you some additional ones to practice. But I think, we're getting so many of Taylor series, that, hopefully you're getting more comfortable, with these. Just want to keep reminding you guys that, a lot of times, not all the time, but a lot of times, the last part, part D, or part C, or part D of FRQs, I do want us to kind of, have that mindset of not getting stressed out if we don't, or aren't able to, feel like we're able to fully answer that part. That's the way that these AP exams are designed, that the last part of FRQ is usually more challenging, more difficult. But treat them like bonus, right? In the sense that you still want to try it, still want to see if you can earn points, but if you don't get it, it's not going to impact your grade, right? If you miss every part D, on the AP exam, you're still in line to earn a 5, right? Because if you missed every part of Part D, you're still earning potentially 5 to 7 points out of 9 points, assuming that you're still that parts A through C are good. Sometimes the hardest part is not with Part D, but generally that's the pattern. They're kind of building. A through C is usually Part C is usually more involved than Part A, and then Part D is usually the more challenging part. So don't get caught up with Part D on the AP exam where you're spending so much time on that when you could be going to something else, right? You try it, earn as much as you can, but then you move on, right? Don't get so caught up with that. Okay, we're gonna see some of that today where Part D is gonna feel like it's a little bit more challenging or than we're used to. All right, so Part A, write the third degree Taylor polynomial for f about x equals 2 and use it to approximate f of 1.5. So we want to center on the Taylor polynomial about x equals 2. So go ahead and fill out the third degree polynomial. And then we can replace all the f of 2, f prime into our polynomial. Okay, so try that. And then I'll show each part once you guys try it. First two terms is just linear equation. After that, your fractions will start appearing in the pattern. Okay, replace all your numerator in function notation with the values provided at the top. Place all your x's with 1.5. Okay. Any questions on part A? Part B, the fourth derivative of f satisfies the inequality that the fourth derivative is guaranteed to less than equal to 3 for all values in x, all x in the closed interval from 1.5 to 2. Use Lagrange error found to show that f 1.5 of y f 1.5 cannot equal to -5. So this is our approximation using Taylor polynomial. We know that this only to the third degree. We know this is not the exact value of f 1.5, but we can have an idea as to how accurate this is if we can figure out the error. So let's go through the Lagrange error bound. So identify your n value, identify your x value, identify your c value. Your n value is 3. Your x value is 12.5, and your c value is set at 2. So we get our maximum error. The fourth derivative, the maximum of the fourth derivative evaluated at z over 4 factorial, 1.5 minus 2 to the fourth. And that error, the worst case scenario for our the accuracy of that polynomial is off by no more than 0.008. So we know that our range of values that f1.5 can be as small as negative 4.96 minus 0.008, and then as large as negative 4.96 plus 0.008. And the maximum that this can be, or the minimum that it can be, is never going to reach -5. So we know that based off of our error bound, based off our approximation, we're able to show that our interval of values that f1.5 can be is going to live between -4.96 and -4.95, and and this doesn't go stretch as far as -5. So we know that f of 1.5 cannot be -5. All right, part C. Write the fourth degree Taylor polynomial for g of x equals f(x squared plus 2. Use P to explain why g must have a relative minimum at x equals 0. So we can just take our polynomial, replace all the x's with x squared plus 2. We only need to get up to the fourth degree polynomial. So once we replace our x with x squared plus 2, this will be up to the fourth degree. So we don't have to go any further than that. You don't have to go as far as I did with g of x. You can leave your the g of x unexpanded. The next part of C says use P of x to explain why G must have a relative minimum at x equals 0. So we have our polynomial version. How do we know that there must be a relative minimum at 0? Well, we know that relative minimum will look like this. And at that point, a couple of things are going on, right? We know that P prime of 0 must be equal to what? 0, right? And we also know it's a relative minimum because we can find the second derivative, and if we can show that the second derivative is what? Second derivative tells us about what? on concavity, right? So as long as this is what? Positive, yeah, as long as it's positive, then if we have these two, characteristics paired up, then we can guarantee there must be a relative minimum. I guess we could also create our, sign line from P prime and show that relative, decreasing to increasing. But I think it's a little bit faster in this case to just fill the first derivative, plug in 0, fill the second derivative, plug in 0. At the first derivative, we should get 0. At second derivative, we should get positive, and these two paired up at the same point ensures that we must be looking at a relative minimum. G prime of X. You can also find G prime from this level here. Just go through power rule, go through chain rule, plus 0, and you're going to get 0. Find the second derivative. Your second derivative at 0 is going to end up being 10, which is, none of it's not that important. It's the fact that it's positive. So the fact that we have a 0 slope and concave up, these two these two characteristics paired up at the same point indicates we must be looking at a relative minimum. Okay, next up, page 18. I think part A should feel pretty familiar. We're just building our third degree Taylor polynomial. Two six. There's my setup for my polynomial to replace all those values with numeric information given to us, and then we can use that to find our approximation. Part B, write the fourth degree to the polynomial, where g equals f of x squared. So replace every x with x squared. Only asking us to the fourth degree, so once we replace this x with x squared, that will be enough to be our last check. Part C, write the third degree polynomial where h equals the integral from 0 to x of f of t dt. So we just take our f of t, and we're just applying power rule. And we're building it off of the original p of x, not f of x squared. So 5 becomes 5x, 3x becomes 3x squared over 2, 1 half x squared becomes 1 half x cubed over 6. The reason that we don't have a plus c here is because initially all this starts off initially as t, and then once we find the antiderivative, we do a half bracket from 0 to x, and only these x terms remain. Everything zeroes out. So the stepped integral doesn't need us for us to involve plus c. Okay, part D, this is what I'm talking about with this is a little bit more challenging here. Let h be defined as in part C. Given that f of 1 equals 3, either find the exact value of h of 1 or explain why it cannot be determined. So h is the integral of f of t. However, understand that this f of t is only an approximation, right? We only have the third degree polynomial. So if we take the integral of this, it's only an approximation. So if we want to find h of 1, we can plug 1 in here and get an approximation, but we're not able to find the exact h of 1. I mean, we know f of 0 equals 5, we know f of 1 equals 3, but the fact that our polynomial is first off just an approximation, and it's centered at 0, so this is not the exact integral for h of x, for exact value for h of x. So we're not able to be defined between 0 and 1 just because we only have an approximated polynomial. For part.
For part D.
Yeah.
At the end, you said like, it's not defined for zeros less than two, so that's 1 point.
Yeah, so this f of t is only is centered at 0, or I mean, we know f of 0 equals 5 and f of 1 equals 3, but we don't know anything between 0 and 1. Since this function f of x was centered at 0, it's it's trying to model after the function at x equals 0, but it's only an approximation, and this is not exact, so we're not able to define it between 0 and 1. Right, write the first degree Taylor polynomial, so we're just doing a linear approximation here. Use this, find, h of 1.9, use linear approximation, plug 1.9 into your, equation for your function line. Is this approximation greater or less than h of 1.9? Well, we know that there's a curve, the function is a curve, we want to know, what is our linear approximation, and we know it's under or over approximation, depending on whether we're where that tangent line is hitting a graph at a concave up or whether it's at a concave down. And we know that our second derivative, right, all four derivatives are increasing, and the second derivative is positive. So we know that's basically representing the graph is shaped like concave up. Basically, h prime is increasing. If h prime is increasing, concave up, it's going to ensure that we're going to get an under approximation.